Dijkstra algorithm is a single source shortest path algorithm. It is used to find the shortest route, the shortest path between two nodes or two locations within a graph. This is mostly used in maps like Google Maps. It is used in social networking websites uh, to find the relationships, or to find, you can say, to give suggestions um, in the social networking sites. And it is also used in the telephone networks, in the fiber networks, ethernet networks, whenever network traffic is moving from router to router, or from node to node. In that case, it needs to find the best possible or the shortest path between the two locations. So this algorithm is the base algorithm for all of that applications. You know that in the graph we have nodes and the edges. Nodes are called either vertices, or nodes, or these are representing the locations, or two things in which between which the relationship or edges are used to denote the distance or the time or anything, any kind of relationship between them, to go from one location to another one. This is represented by a no, an edge. Now in the paper you will be given a full graph, and you will be told about a starting node and the ending node, and you will have to either find a path from the starting node to the ending node, or to all the nodes you have to find one value. Now these numerical values, these are called costs. This could be time, it could be distance, or technically any kind of relationship. It's basically the weight of the graph. These are the weighted graphs that are used, and these values, these are in these algorithms, shortest path algorithms, these are called the cost. The cost of traveling between the two nodes, for example, from A to B is 5, from B to F is 3. Now we'll be looking at the steps that you have to follow. Your task in this example, is to find the path to all the nodes. You will be given a work area, and you will be given a table to provide the final values. The table will look like this: the nodes and the values to it. Now there is one more thing that you can add in your table, although not required, but if you need to find the shortest path to one single node, so this value will help you in that case. I will explain when we are doing the example. Now the first step that you have to do is to assign 0 to the starting node or the starting vertex, which in this case is A, and the rest values should be infinity. Now infinity means that we don't know the value it will be, or it's an unknown value at that point. So infinity in this case. So 0 to the starting vertex and infinity to all the values. So let's update. Now this working needs to be shown on your paper as well. You can have it. Now in this table you can just erase these values and update them as you go on, but your graph or your work area should have the working, and when you're cutting and writing the new values. Now our starting node is A. What you have to do is, we'll go from A to all the connected nodes, which are B and C in this case, and we are going to update the value based on the cost. So cost of moving from A to B is 5, so we change this to 5 and this to 6, and also you're going to do this over here, 6, no, so this was, and 5, this was infinity, and the last node that we reached to the node, to a specific node, we're going to write over here. Again, this is not required mostly, but this will be useful. Second step is that we have to go from all the nodes and we have to visit all the nodes. Now from A we visited B and C, which were connected to A. At this point we say that we have processed A, or we have visited A. That means in our list of the processed nodes, first of all let's make the list of the unprocessed node A, B, C, D, E and F. Now once we are done with A, we are going to remove it from there and add in the process node. Why do we need to keep a track of this? Because for example, when you are at C or when you are at B, do you come back to A? No, because we already gone through it, we have already visited it, so technically we don't need to go back. But when we say that we have to visit all the connected nodes, so you need to skip those who with the nodes that have been processed. Then the next step, let's just erase these values first. Okay, yeah, E over here. Now select the node with the smallest value. When we are done with A, the next nodes are B and C. And which node we have to move, we have to go next, that the values of the nodes will decide. So B has 5, C has 6, so we will now next look at B. We came to B, you can use another color to mark your, we went to B. Now at B we have how many nodes connected to it? A, E and F. Now again A is already processed, we are not going to look at it, so we are going to look at E and F. Now E's cost is 7, so whatever cost of the node B is 5 plus 7, that will be our cost for E, which is 12. The same as 5 plus 3, F will become 8, and we are going to update our values over here as well, which will be 12 and 8, and the visited node was B. Now we are done with B and we write its name in the list of visited. We are done with B, visited nodes. Now let's look at what's next. The next should be the least one. Let's circle this, so we are done. We have 6, 12 and 8. So 6 is the least. We are going to look at it next. So from 6 we have D and A. So A is already processed. Let's not look into it. So 6 plus 4 becomes 10. This changes to 10 over here, and we change the value of D to 10, and the previous node was C. And now we say that we have processed C, or you can have over here as well. Now the next nodes are 10, 8, 12 and 8. 8 is the least one, so we will look at F node for now. F has the nodes connected B, E and D. Now B is already processed, so let's not look into it. From F to E the cost is 4, so we'll add 4 and 8, which becomes 12. Already the value of E is 12. So the rule of updating a value is that we only update if the new value is smaller. So we don't change it. It's equal, we don't need to change it actually. Then F to D, 7 plus 8, which is 15. So the new value is greater than the old value, which was 10. So we don't update it. Now we say that we have looked at all the nodes connected to F, so F is now processed. F is now processed and its value is 8. Now left is D and E. Out of these, D has the smallest value, so let's look at that. D has connected nodes E, F, D. Out of all the unprocessed nodes we have E, so 10 plus 6 is 16. Going from D to E is 16. So already the value of E node is 12, so we don't update it, and now we say that D is processed and the value of E is not updated. Now the previous node of D was F. Now I will tell you in a moment what these last node values will be good for. Now at the end we have E left, already everything else is processed, so technically E is also processed. We don't need to look at any other values. All of these are now visited. So our final values are 5, 6, 10, 12 and 8. Now this is when you need to find the values of all the nodes or the shortest path to all the nodes. What if you need to find the path from A to F? So which one is the smallest path? Now when we are calculating it, we kept a track of the last node. Now last node should be F, so we look at F. From F we came from B, so from B we came from A and we went to the starting node. So our path should be, again highlighted with this, A to B to F, and the cost of reaching F should be 8. This should be the shortest path. You can also see that we have the path A to B to E to F, or A, C, D, E, F, A, C, D, F. Out of all of these, the shortest path is A, B, F. Now by chance this is actually the shortest path with the least amount of these number of nodes, but it will not always be the case. It could be different. It could be the highest number or the highest cost, and the more nodes could have the least cost. But for now in this example, this is the shortest path to reach to the endpoint, or these are the values of all of the vertices or the nodes.